In this video, we're going to be looking at the second part of topic 17b, the transition metal reactions, and we're going to be focusing on the remaining compounds that we didn't look at in the first one, and this is going to be part of the IAL chemistry course from Edexcel. So we'll be looking specifically at the reactions for vanadium, chromium, nickel, manganese and zinc, and we have to go into a little bit more detail with regards to vanadium and chromium and also look at the redox reactions of those, whereas we're looking at the reactions of the remaining transition metals with sodium hydroxide and ammonia. So just a reminder, there are 4 different types of transition metal reactions that we can see with the complexes. The first one is redox, where we get a change in the oxidation number. So for example, from iron 2 to iron 3. Deprotonation is the most common one that we come across, and this is where one or more of the ligands loses a hydrogen atom. Ligand exchange is when one or more of the ligands is replaced with something else, and we see this when we add in generally the excess sodium hydroxide or excess ammonia, and if we have a change in the number of ligands, then we class that as a coordination number change. These two are the most common, and these are the ones that you have to know in detail in terms of the colours, but we will also look at some redox reactions as well. So we're going to start by looking at the chemistry of chromium. Now, the majority of the reactions of chromium are very simple, similar to copper, cobalt, iron 2 and iron 3. The biggest difference is the fact that chromium has ions which can have an oxidation number of +6. So we have to consider these reactions in a very different way. And in particular, this is when we look at the redox part of it, when we have these ions that have this 6+ oxidation number. Now, the colours that we use in this video and what is used in the Edexcel specification may differ slightly when you read it online or in different textbooks, because of course colours are subjective. The colours that are mentioned in the video and in your textbooks or your notes, these are the ones that you should be referencing in the exam, because these are the ones that Edexcel use. So if you do read it elsewhere and you see a slightly difference in colour, that's okay. Just make sure that you use the colours that Edexcel want you to. And chromium compounds in terms of the colours, are often complicated by the fact that a solid and a solution of the same ion can have different colours, and they can also be affected by the amount of oxygen that is dissolved or the concentration of oxygen. So chromium is a little bit more of a challenging one. But we're going to start off by looking at the reaction with sodium hydroxide, similar to what we've looked at previously, and this is a deprotonation reaction. So we have chromium 3+, when it's hydrated, this green solution reacting with 3 moles of the sodium hydroxide, and we get 3 of the ligands remaining as water and 3 of the ligands becoming hydroxide and making 3 water molecules. This is very similar to iron 3 with this deprotonation reaction, and it's the fact that we have these 3 hydroxides because it's the same as the charge. When we react this same substance with aqueous ammonia, we get that exact same complex. So we have the chromium with its 3 waters and its 3 hydroxides, making this time 3 ammoniums. And we still see that same green precipitate. Now, when we take that green precipitate and we add excess sodium hydroxide in varying different amounts, which we'll see here, we get that precipitate dissolving, and then further excess sodium hydroxide gives additional deprotonation. So we can get this complete deprotonation process happening until it happens to all of the ligands. So when we add 1 more mole, we're going to have the H2O coming down to 2 ligands, with 4 of them being deprotonated, and that gives you a charge of 1-, because you now have 4 hydroxides versus a 3+. And of course we make a water, and that gives you that green precipitate dissolving into a green solution. And if I add even more sodium hydroxide, so another 2 moles, I can deprotonate all of my substances, all of my ligands, down to the hydroxide, and that has a charge of 3-. So that excess sodium hydroxide can give you that further deprotonation, and we're just simply changing the precipitate into a solution, but we don't see any other colour being produced here. It still stays a green solution. And when it reacts with the hydroxide ions, we can reverse these by adding in some acid, and we talked about that in the previous video where we talked about amphoteric hydroxides, and this is an example of that. So that neutral complex is an amphoteric substance. If we take that green precipitate that we had made previously, so the chromium with the 3 hydroxides, and we add this time excess ammonia, this green precipitate will still dissolve, but it's a little bit slower, and eventually it will dissolve to form a purple solution where we get a ligand exchange reaction happening. So we have this, all of the ammonias swapping out, and we are left with 3 waters and 3 hydroxides. So this time we see a big change in the colour where we go to a purple solution. Now, in all of the previous reactions, the oxidation number of the chromium has remained unchanged at +3. But we know that chromium can have varying oxidation numbers. And if we actually want to change the oxidation number, we can do this by adding hydrogen peroxide, because the hydrogen peroxide acts as an oxidizing agent, causing the ion to change from a 3+ to a 6+. This change in oxidation number then gives us a change in colour, where we go from a green solution of the 3+ to a yellow solution of the 6+. So our equation is completed to show the chromium, which has in the oxidation number of 6+ plus 8 waters and 2 hydroxides. Now, when we have chromate the chromium in this 6+ ion, the chromate ion is stable in alkaline solutions, but in an acidic condition, the dichromate is more stable, so where we have Cr2. So if we add a little bit of acid to this yellow solution, we will see a colour change going to orange. And this can be easily reversed by adding some more alkali to go back to being the yellow. And this is an example of a redox reaction. Now, when we write out a redox reaction like this, it's much easier for us to leave out any ligands that may be there that don't undergo the redox reaction, in particular water ligands, because if they don't take part in it, all they do is they just overcomplicate the expression in the equation. So we don't include any ligands similar to spectator ions that don't take part in the reaction. Now, when we take this dichromate and we have this acidic solution of it and we add zinc metal to it, we will see a reduction reaction where we're changing the oxidation number of the chromium from +6 down to +3 down to +2. And each of these has a different colour associated with it. So we go from orange when it is in the +6 to green when it is in the +3 to blue when it is the +2. And this is all happening because we're getting this zinc reacting and reducing the oxidation number. So the zinc acts as a reducing agent and the chromium is then reduced from +6 to +3 to +2. Now we can determine which of the redox reactions of chromium will happen using our E0 values that we learned back in topic 16. So you can see that we have got 5 equations here, and we're going to look at specific reactions and see will these happen and show that these are feasible due to these E0 values. So you can see we have zinc, plus we have equations number 2, 3 and 5, which are the chromium reactions, and then the hydrogen peroxide. And remember, the best reducing agents are on the top right, and the best oxidizing agents are on the bottom left. So if we start with the first redox reaction, this is the oxidation of chromium 3+ to chromium 6+, and this involves the equations number 3 and 4. So because equation number 3 is more negative, this is going to be the left-hand side, and the other one is going to be the right, meaning this equation is going to go that way in position of equilibrium, and this equation is going to shift that way. Therefore, we get an E0 value which is positive, telling me that this is thermodynamically feasible. Remember, your E0 cell is the right minus the left. And because this is a positive value, it means it is thermodynamically feasible. In other words, the hydrogen peroxide will react with the chromium in order to make the chromium hydroxide in order to make this chromium 6+ ion. And then if we wanted to form the dichromate, then we could acidify it. So this is just backing up the reaction that we've just looked at. In terms of the reduction reactions and how these work, we can see that we're using equations number 1 and number 5, and we want this reaction at the bottom, number 5, to go to the right-hand side because we want to go from Cr2O7 to the chromium 3+, and we want the zinc to be going to the left to go from the zinc to the zinc 2+, and that matches up with our actual values because remember the more positive value is going to be the right hand side and the more negative value is going to be the left hand side. So because our positions of equilibrium are moving in the direction that we want them to, this is also thermodynamically feasible because we will get a positive E cell value here. When it comes to the reduction from chromium 3+ to chromium 2+, the same thing happens. We want to go from the 3+ and the zinc. So we circle the 3+ and the zinc. If you remember, we talked about this in topic 16A when we were looking at thermodynamic feasibility. And we want this reaction to go to the right and this reaction to go to the left. So if we look at the values, the more negative goes to the left-hand side, the more positive goes to the right. Again, we get a positive E0 value, so this is a thermodynamically feasible reaction. In other words, zinc can reduce chromium from 6+ to 3+ to 2+, and we can back this up by viewing the colour changes and also looking at the E0 values. And that's the summary that you're going to have to know. So looking at what we start with, and then the different reactions. So what happens when we add sodium hydroxide and ammonia, we make this green precipitate. And if we add excess, we make the green solution for the excess sodium hydroxide, whereas it's a violet or purple solution for the excess ammonia. And then looking at the reduction and oxidation reactions of the chromium as well and the associated colour changes. So it's very important to know all of this. And you can actually see the different reactions here as well. So the first tube has got our hydrated chromium 2+ ion, so it's a very, very pale blue colour, and then that's what's produced at the very end with that reduction of zinc. Tube B, this sort of slightly darker blue colour, is the chromium 3+. The tube C, the sort of green one, is the chromium 3+ when it's present in an alkaline solution. And then D, both contain chromium with the oxidation number of 6. So the orange one is the dichromate and the yellow one is the chromate 6, just on its own. Now if we move on to the manganese reactions, again, we're just going to be focusing here on the main reactions with sodium hydroxide and ammonia. There's only a very small part of this that you have to know. So when we take this pale pink solution of the hexaaquamanganese 2, we get a deprotonation reaction happening. So very similar to what we've seen in our previous reactions, where we have 4 water ligands, and then 2 of them becoming hydroxides, and we form 2 waters. And this pale pink solution gives us a pale brown precipitate. And when this pale brown precipitate is then oxidized, it changes to a very dark brown precipitate and then eventually just forms manganese dioxide. And you might actually see this if you are using something like potassium permanganate. If you get potassium permanganate onto your skin, it will leave a brown stain or a brown residue, and that's the precipitate of the manganese dioxide. When it reacts with the aqueous ammonia solution, we still see that same precipitate being formed. So we have our manganese with our 4 waters, and our 2 hydroxides, but this time, of course, making the 2 ammonium ions. The biggest difference here compared to our other transition metals is this will not dissolve when we get aqueous sodium hydroxide or ammonia being added. So the pale brown precipitate is where it stops. The only time it will ever change colour is if it undergoes further oxidation in air. Now, vanadium is another one that's a little bit more complex because it is very similar to chromium in the fact that you can have 4 different oxidation numbers here, whereas chromium could have 3 different oxidation numbers. And depending on the different oxidation number will give us a different colour. You have to know the formulas, the associated oxidation number, and the associated colour. Now, the good thing with vanadium is we don't have to discuss its reaction with the aqueous sodium hydroxide and aqueous ammonia. We are solely looking at the redox reactions where our oxidation number changes. So we're looking at their feasibility using these E0 values. So if you have vanadium 2, it is purple. If you have vanadium 3, it is green. Oxovanadium 4 is blue, and dioxovanadium 5 is yellow. So all depending on that oxidation number of the vanadium, we will see these different colours. And you can see each of them here. So we've got our +5 oxidation number being the yellow, +4 being the blue, +3 being the green, and +2 being the purple. And we can actually get this gradual reduction from this oxidation number of 5 through the different colour changes down to an oxidation number of +2. And you can actually see the different colour changes. Now we can determine which of these redox reactions are going to happen using these E0 values, very similar to what we did with chromium, and we can show that which ones are feasible and which ones are not, just to prove that we get these different colour changes. And remember, again, your best reducing agents are on the top right, and your best oxidizing agents are on the bottom left. And we've got 5 different equations here. We have 4 of them, which are for vanadium, and 1 for zinc. Now, we were going to look at very similar to what we did for the chromium, but we're just going to condense it slightly, but it's the same concept each time. So we can have a reduction, first of all, from the +5 down to the +4, and this is possible using zinc. So we take our 2 half equations. We know that the zinc is going to have to be oxidized, and the vanadium is going to have to be reduced. So we've taken equation number 2 here and we have reversed it. We always want to have equation number 2 as the left-hand side because we want that oxidation to be going in that direction to zinc, from zinc to the zinc 2+. So we want all of the others to be going from left to right. We want each of these to be the right-hand side electrodes, and then we can work out the E0 cell by doing right minus left, and that tells us about the feasibility. So if we go back to the 5+ to the 4+, our zinc going from the zinc to the zinc plus, so it is going our position of equilibrium shifting to the left, whereas for our 5+ to 4+ vanadium it's shifting to the right. That gives us a value for E0 of 1.76, which is positive, so that is a thermodynamically feasible reaction. So we will see that one happen, and we see a colour change from yellow to blue. For the 4+ to 3+, again, our zinc is still the one that is being oxidized, so that's not changed, but now we're going from the VO2+ to V3+, and when we combine those 2 things together, we get this overall redox reaction that gives us an E cell value of 1.1. So this is a feasible reaction, and we see a colour change from blue to green. For the 3+ to the 2+, we have the zinc still being the thing that is going to be oxidized, and then our reduction from 3+ to 2+, and the overall reaction gives us an E0 value of 0.50, which is, again, positive, so that's thermodynamically feasible. So here we will see a colour change from green to purple. Now, where it changes is when we have this zinc trying to oxidise the vanadium 2+ to vanadium metal. And this one we can see is going to go against our positions of equilibrium. So the E0 value for the vanadium 2 plus to the vanadium on its own is minus 1.18, whereas the zinc was minus 0.76. Now, we've always said that the more negative is going to go to the left-hand side. So if this minus 1.18 went to the position of equilibrium, moved to the left-hand side, that means that we're not going to be favouring the change from 2 plus to 0. In other words, zinc cannot act as a reducing agent for vanadium 2 plus to vanadium metal because its E0 value is more positive. In order for the zinc to be the thing that is being oxidized, it must have the more negative E0 value. So this reaction is not thermodynamically feasible. Moving from vanadium now onto nickel. Nickel can react again with our aqueous sodium hydroxide and aqueous ammonia. These are the main things that we want to look at. And this hexaaqua nickel 2 is a lovely green solution, and it undergoes the same deprotonation reaction that we've seen now multiple times to form our new complex with 2 waters, and this is a green precipitate. So notice every single time we're doing this deprotonation, we are making a precipitate, and the sodium hydroxide and the ammonia will make the same precipitate each time. So when we react it with the ammonia, all that's changing is what's in the actual equation. So we make that same complex, but we form 2 ammoniums. Now where they vary is what then happens when it's in excess, and there's no change for the sodium hydroxide in excess, but when the ammonia is added in excess, we get a ligand exchange reaction happening, and this green precipitate swaps out all its ligands for the ammonium ligands, and that gives a charge of 2+, because of course the ammonia is neutral, and then we make the 4 water ligands and the 2 hydroxides, and this forms a deep blue solution. So we're going from a green solution to the green precipitate, and then when the ammonia is in excess, we're changing now to a deep blue solution. The last one that we're going to look at is the reactions of zinc. Now zinc, remember, doesn't have that empty d orbital, so we don't get those dd transitions. Therefore, all the zinc complexes are all colourless when they're in solution, or they are white precipitates, because we don't get any of these dd transitions to give us this colour. So zinc, when it is a 2+ hydrated ion, or this hexaaqua zinc 2 is a colourless solution, we do still get that same deprotonation happening, where we have 4 water ligands and 2 hydroxides making 2 waters. And when we add in an excess of this sodium hydroxide, we can then take that white precipitate and dissolve it into a colourless solution. So this excess takes away 2 more hydrogens from the waters, so giving us only 2 water ligands left and 4 hydroxides, so further deprotonation plus 2 waters. So we're going from a colourless solution to a white precipitate, and then excess sodium hydroxide, dissolving that back into a colourless solution. Now, zinc hydroxide is amphoteric, so it can also react with acids. You don't need to go into too much detail about how that happens, unlike what you had to do with the chromium. The last reaction is then looking at when we get this excess ammonia. So when it's excess ammonia, we still get that same deprotonation happening to make this white precipitate complex, where we have the 4 water ligands and the 2 hydroxides. And this time we're making the 2 ammoniums. But when we get this excess ammonia, we get a ligand exchange. So with sodium hydroxide, it's further deprotonation, but with ammonia, it's a ligand exchange. And here we get zinc giving us the complete exchange of ligands and going back to being a colourless solution. So in summary, when we have this ion starting, you need to know the colour of the solution of that ion, what happens when we add in the aqueous sodium hydroxide, so what precipitate we make, and then what will happen when we add in aqueous sodium hydroxide in excess. And you can see that the only ones that have a reaction are chromium and zinc, but you need to be aware of all the different colour changes that we can have here. And you also need to be able to do the same thing for aqueous ammonia, where you notice that the colour of the solution and the colour precipitate does not change, but when you add the excess ammonia, we can get some different substances being formed. So whereas chromium makes the purple solution, cobalt makes the yellow solution, nickel and copper both make deep blue solutions, and the zinc makes that colourless. So these two tables are extremely important for you to know. So let's finish off with some past paper questions. We're going to look at a question about chromium and then a longer question about vanadium. So chromium is in the D block of the periodic table, and it is a transition metal. When a few drops of aqueous ammonia is added to an aqueous solution of chromium 3+, a green precipitate of chromium 3 hydroxide is formed. We want to complete the ionic equation for this particular reaction. So when we make when we add in the ammonia, remember we're getting deprotonation happening here. So we are removing 3 waters, or 3 hydrogens from the waters. So we would be left with chromium, H2O3, OH3, and that would give you a neutral complex, and we make 3 ammoniums, and that then requires 3 ammonias to start. So remember, anything that goes from a 3+ is going to react with 3 moles of the substance. If it is a 2+ oxidation state, it will react with 2 moles of the substance. So chromium and iron 3 are the two that you need to remember that there is that slight difference. And chromium 3 chloride can exist in aqueous solution with 3 possible complex ions. And for complex Z, this bottom one here, where we have 2 chlorides and 4 waters totaling 6 ligands, we can have 2 possible structures. And we want to be able to show the diagrams to complete the 2 possible structures. And essentially what this is you're going to have the chlorine either being side by side with something else, with another chlorine, or being completely separate from each other. So we can have the chlorine next to each other, and it doesn't matter where you put the chlorine. If it's on the left hand side at the top, that's still the same complex. The left hand side at the bottom would be the same if the chlorine was at the bottom. So we want to have them either side by side or completely separate from each other, and then we add in our 4 water ligands. And remember, you must always show that the water ligands are being attached to the oxygen and not to the hydrogen. So any on the right hand side should be written as OH2, any on the left hand side should be written as H2O. And you can see here how the marks are breaking down for each of those. So for the first part, you get the correct formula for the chromium 3 hydroxide and then the rest of the equation. And for the second part, it was 1 for each of the 2 complexes. Now, the vanadium question is quite a large question, and it is a very typical A-level style question because it's 7 marks. And you can sometimes see a question like this and become very overwhelmed, and that's absolutely normal. The best way to approach a question like this is to break it down step by step and think about what you're doing. Now, obviously, when I'm going to write it out here, isn't quite how you would write it in an exam, because you should be writing it out sort of in sentences, but I'm going to go through more to do with what should be going through your head and how you then translate that to the paper. So we have excess zinc powder being added to an acidified solution of the compound NH4VO3, and using the data in the table, we want to explain the sequence of reactions that takes place. In your answer, you should include a description of what you see, so the observations of the colours, that's the first thing that you need to be thinking about, the relevant ionic equations, and then their calculated E cell values. You don't need to include any state symbols in your equations, but you should be stating what is happening. So with a 7 marker like this, the best place to start, first of all, is identify what's actually reacting. So this is vanadium. We know that we can have 4 different vanadium substances. So we're going to be looking specifically at each of these. And first of all, figuring out the oxidation number and the colour. So the oxidation number for the bottom one is going to be +5, then +4, +3, and +2. And the colours for each of those, you should be able to say the +5 is yellow, the +4 is blue, the +3 is green, and the +2 is purple. So by writing out the different colours that you have and by identifying the oxidation numbers, that alone can be getting you the first 2 to 3 marks, because what you're saying is that these are each of the colours and this is what you see. So what's happening is you're going from a +5 complex down to a +2 complex. So that is the statement. So the identifying the colours gets you the first 2 marks, and then the statement would be that zinc acts as a reducing agent and the vanadium is moving from a 5+ to a 4+ to a 3+ to a 2+. That's your third mark. Marks 4, 5, and 6 are then your equations of what's happening. So you're looking at what is the combinations here. And remember, if you want your zinc to be the thing that is acting as the reducing agent, it must be the most negative value. This must always be the left-hand side, or the most negative. So if we look at the first reaction that we want to happen, we want the zinc always to be going from the zinc to the zinc 2+, so that's always going to the left-hand side, and we want to start with going from the 5+ down to the 4+. So we're going to have to multiply each of these by 2 because we need to have 2 electrons. So I'm going to have the zinc metal reacting with 2 of the VO3- plus 8 hydrogens. Of course, we remove the electrons. That's going to give us the zinc 2+ plus 2 of the VO2+ plus 4 waters. So that is going from a 5+ to a 4+ vanadium. And our E cell value is going to be right minus left. So 1 minus 0.76, giving me a value of plus 1.76 volts. That's mark point number 4. Mark point number 5 is now looking at the next reaction. So we want to go from the 4+ down to the 3+. So we're still going to be reacting the zinc. That's not changing. This time we're going from the VO2+, and I need 2 of them because I need to multiply all of my electrons again. This time plus 4 hydrogens is going to give me the zinc 2+ plus 2 vanadium 3s plus 2 H2O. So this time going from the +4 to the +3, and my E cell value is going to be the right-hand side, which is the plus 0.34 minus 0.76, which is a value of 1.10 volts. Now to get mark point number 6, we're looking at the +3 going to the +2. So we're looking at the green equation here, so from V3 plus E to give you V2 plus, which is minus 0.26. So again, we have the zinc as normal plus the 2 V3 plus, and this time giving you zinc 2 plus 2 V2 plus. So that's changing our oxidation number again. And this gives you an E cell value, again, right minus left, which is going to be minus 0.26 minus 0.76, which is 0.5 volts. And to get the 7th mark, you have to then say that it does not go any further than that. So we don't get any reduction for the 2+ down to the V metal. So we get no further reduction to the vanadium metal as the E0 value is more negative than zinc. So because the E0 value for that change from 2+ down to the 0 oxidation number is minus 1.18, that would not be a feasible reaction, and you can either state this, you can work out the equation and show the E0 value to be a negative number, anything to show that you understand that the reaction stops there. So there's quite a lot of information that is required from you here, but once you start to break it down into the smaller parts, it becomes a little bit easier. So start off by identifying what is the oxidation number of each of them, and look at what is the oxidation number of the first thing in each equation. From that, then what are the colours? And now you know that you should be going from a sequence of 5+ to 4 to 3 to 2, and what are the associated colours with that? And then writing out the equations with their calculated E cell and showing you understand that it stops at vanadium 2+. And you can see exactly how it breaks down here as well. So this is a 7-mark question, but once you get this and you practice it, this could be actually a very good 7-mark question, because you can pick up quite a few marks just by knowing the oxidation numbers and the colours and being able to calculate an E cell. That's everything for topic 17b, the transition metal reactions. If you have any questions, please do feel free to leave a comment below, and we hope to see you back soon.